Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So this is video part 4. So in this video we will continue discuss on Langmuir isotherm. Before this, we have discussed derivation of Langmuir equation where the adsorption only occur at one site per molecule. So this is also known as associative adsorption. Okay, associative adsorption is when a molecule adsorb without fermentation. Okay, now let's consider derivation of theta for dissociative adsorption. Dissociative adsorption is when the molecule dissociate into their atoms upon adsorption. That means for each adsorption process, the molecule will occupy two surface sites as shown in this figure. Okay, here one molecule hydrogen once adsorbed on surface, it will dissociate into two hydrogen atoms and occupy two surface sites. Since the surface has to accommodate two species, then the rate of adsorption is proportional to the square of the number of vacant sites. So the adsorption rate, R adsorption equals to d theta over dt equals to Ka P and 1 minus theta squared. Okay, the rate of desorption now depends on the reassociation of two species on the surface. So R desorption equals to d theta over dt equals to Kd times N times theta squared. Okay, same as before, at equilibrium, the rate of adsorption equals to the rate of desorption. So rearrange the equation. Finally, we get theta equals to square root of Kp over 1 plus square root Kp. Okay, let's see the variation of surface coverage with the pressure. Okay, we know that theta equals to Kp over 1 plus Kp. Okay, then when we plot theta versus the pressure, we get a plot like this. Okay, at low pressure, we can neglect the term Kp in this denominator. So it equals to 1. Therefore, theta equals to Kp. Okay, as shown in this figure, at low pressure, the amount of gas adsorbed on surface is strongly depends on the pressure of the system. Okay, meanwhile, at high pressure, the denominator here, 1 plus Kp, is equals to Kp. Therefore, theta equals to Kp over Kp, which is equals to 1. Okay, as shown in this figure, at high pressure, the adsorption is saturated, which is theta equals to 1. Okay, that means all the surface sites are fully occupied with monolayer adsorption. Okay, as mentioned before, Langmuir is limited to only monolayer. That's why the plot shows a plateau at high pressure. Now let's see the variation of surface coverage with the equilibrium constant K. Okay, for a strong adsorption, Ka is greater than Kd. Then K, the capital K, is greater than 1 and theta equals to 1. Okay, as shown in this figure, for a strong adsorption, the curve quickly achieves a plateau with increased the pressure. Okay, meanwhile, for weak adsorption, Ka is less than Kd. Okay, that means K is less than 1 and theta equals to Kp. Okay, as shown in this figure, for a weak adsorption, the theta is slowly increased with increased the pressure. This is because the gas molecule like to be in the bulk phase rather than to be adsorbed on the surface. The equilibrium constant K is both temperature dependent and can be related to delta G and hence to the enthalpy change delta H of the process. So at a given pressure, the rate of adsorption is determined by the value of K, which in turn depend on both the temperature and the enthalpy of adsorption delta H. And the value of K can be related to delta H by using Van Hoff equation as shown here. When theta is constant, the Langmuir equation can be simplified as theta times 1 plus Kp equals to constant, which is equals to Kp. So that ln K plus ln P equals to constant, and so ln P equals to minus ln K. And then divide this equation with delta T. So we get d ln P over dt equals to minus d ln K over dt, which is equals to minus delta H over RT squared. With d1 over t over dt equals to minus 1 over t squared, this expression can be rearranged, and finally we get ln P equals to delta H adsorption over R times 1 over t plus C. So this equation is known as Clausius-Clapeyron equation. And then at different temperature, this equation becomes ln P1 over P2 equals to minus delta H adsorption over R times 1 over T2 minus 1 over T1. And finally, we can determine the value of delta H adsorption by using this Clausius-Clapeyron equation by plotting ln P versus 1 over T. And then it will give us a straight line plot with the slope of the plot equals to the delta H of adsorption. From the previous slide, we can conclude that by using Langmuir isotherm, delta H is constant with the change of surface coverage theta. Okay, there are other isotherms which explain the relation between delta H and theta. For example, Temkin isotherm, which assume that the adsorption enthalpy, delta H, decrease linearly with surface coverage. Okay, this figure shows the difference between Langmuir and Temkin isotherms, where in Langmuir, delta H is constant, while in Temkin, delta H is linearly decreased with theta. Meanwhile, the Freundlich isotherm assume that the delta H is exponentially changed with the surface coverage, where theta equals to Kf times P power of 1 over n, where Kf is constant, which depends on temperature, and n is integer and greater than 1. So this figure shows the variation of delta H with surface coverage using both Langmuir and Freundlich isotherms. Okay, as usual, so these are some exercise for this topic. So please answer and then submit in e-learning. Okay, that's all for now. Thank you.